In this lecture, we will discuss about dimension reduction and sparse representation. So, let us first understand that what is meant by dimension of a data. Consider a set of data points as shown in the slide, that it is a set where xi is a data point in the space of n dimensional real space. We can consider it is a vector in that real space. So, the dimension of that space is naturally n. Now, does it mean the dimension of the set S is also n? So, let us take this example. So, it is a 3-dimensional space and there are 4 data points. Now, they may be arranged in such a way that they lie on a plane. So, when they lie on a plane, we can always define a coordinate system within that plane and use that coordinate convention to represent every point. So, in that case, all the points could be represented as a set of points on a 2D space, or which is a 2D real space. So, it is not necessary that dimension of data would be the same as the dimension of the space. It could be lower than that number, but the example has been shown here. So, the principal component analysis is a method by which it finds the minimum dimensional subspace for representing data. So, we will learn in this lecture how this analysis could be done, and the basic idea here is that it computes a new set of orthogonal axes, and using that new set of orthogonal axes, you define new coordinates with respect to the representation. So, it is a coordinate transformation in one sense. What principal component analysis does? It maximizes variance of a component. Let me explain that. You consider a feature vector representation of that data point x, and since it is represented in n dimensional space, so we have n components or n fields of the vector, which is shown here as x1, x2 to xn. This is a convention we are using for representing a data. Now, variance of a particular component, say ith component xi, that is defined as using this mathematical expression. This should be clear that if there are n such data points, that means capital N data points. So, for any xi's vector, the corresponding jth data point we consider that is a value for the jth component of xi's vector, and you consider the mean of that component. So, this is how the variance is defined, the standard definition of variance. Now, we say a component is dominant out of all these n components whose variance is the maximum. So, that is then we say that component is a dominant component. Now, PCA, it maximizes the variance of the dominant component. Let us understand what does it mean. Consider a unit vector W, and since as I mentioned that there is a coordinate transformation involved in PCA, what we can do that we can perform certain type of coordinate convention. So, center of the coordinate or origin of the coordinate can be considered as the mean of these feature vectors. So, let us represent that mean by this S bar, which means you have n feature vectors, say this is x1, x2 like this, say xn, n feature vectors, and S bar should be 1 by n sum of xi I equal to 1 to n. So, this is how the mean could be computed. So, for every x j translated to the mean vector, compute the component along W. Suppose you consider these are the data points and this is S bar. So, we are translating, and this is say the coordinate, original coordinate of the space. So, first we transfer the center to S bar, take any particular direction, say this is the direction W, and take the component, means the dot product of this W. This is a unit vector. This should be an unit vector, and so the dot product of this, that would be the component. That is how we will be computing it. So, this is what is y j. So, if this is x j, this is y j. This part is y j, which is x j minus S bar. So, this is a vector, this is x j minus S bar, and this is the direction of W. So, you take, and which is an unit vector in this case, we consider this is an unit vector, and then you take the dot product of this, then you get this component as y j. Now, you consider the variance of this component. So, the problem of PCA is at least you have to find out one such direction where it maximizes the variances of these projections of different vectors, all the data points centering at its mean. So, let me continue that with that representation. We have a set of data points, and now we are representing the data points in this way, that if I have x j as a vector, then for the jth vector there are small n number of components, and each one component is a variable which is indexed as, the ith component should be x I j. That is how we are representing it. So, we consider ith component as x I j here. So, the mean vector, as we discussed, is S bar, which means this is the mean of each component. We have defined it earlier also, and then we perform this transformation. We are taking the component along a vector W, which is an unit vector, and you can see that every vector is translated towards mean, and for all n vectors there are n numbers. So, for every vector translated it, and we have the corresponding component along the unit vector. So, finally, you get capital N observations or projections of all these data points along W, centering at the mean of the vectors. So, now you consider the variances of these y's, which can be represented as, so we can write compute W, which maximizes 1 by n y transpose y. Actually, you can see that since we have translated it towards mean, so the mean of the y's would be 0. So, it is sufficient if I simply maximize the square of the magnitudes of that vector. That is what is y transpose y, which means this can be written as sum of y I square I equals 1 to n, because the mean of the y, if I consider y I bar, that is equal to. So, we are maximizing the this particular factor y transpose y, and y transpose y can be written as y 1 y 2 to y n, and this is y 1 y 2 to y n. So, this is the magnitude of this vector, that would be sum of y square I equal to 1 to n, and we are taking the mean of it, which is the variance of this value. and if I consider the mean of these y ones, mean of the y ones, or we can write y bar, which is 1 by n sum of y I, that should be equal to 0, because it has been transferred to me. And effectively, we are finding out the variance of the components, and we would like to get W which maximizes this particular factor. There is a constraint on W we have already mentioned, that it has to be a unit vector. So, we should have the norm of the W that should be equal to 1. And effectively, if I consider expand Y transpose or Y is, it has been shown, it has been X transpose W. So, this can be written in this form, and which is giving the expression as W transpose X tilde X tilde transpose. So, this is a quantity which you should note. This quantity is interesting, because what it is measuring the covariance of X. Of course, you have to consider the averaging of those values. So, this is the averaging, this is a term which is divided by n, which will average it out. So, we have to compute W which maximizes this particular factor, and as I mentioned that this is nothing but the covariance matrix C, where the element of say kth lth element is covariance between the kth component and lth component, covariance between kth component and lth component of the vectors of the data points, and that is how the covariance matrix is defined. So, the objective function you can consider for maximizing the variance is that to maximize a function which is the function of weight vector W or the directions, unit directions W, and which will maximizing this quantity. This is the quantity which is same as this one, which has to be maximized, but there is a constraint. So, this constraint in the objective function can be incorporated using Lagrange multiplier, and this is that particular term. So, this lambda is the Lagrange multiplier. So, if I take the derivative with respect to lambda, it will be W transpose W equal to 1, which is actually enforcing the constraint what we want to for while getting a solution. And then if I take the partial derivative with respect to the weight direction W, unit vector W, then we get this system of equations. As you know that I earlier also mentioned that the similar properties or similar rules of differential geometry for one dimensional variable can be extended for multidimensional space also when you are using matrix operations, linear operations. So, you can consider W transpose C W, it is a quadratic product. So, you get 2 C W, and from here you get simply you get 2 into then W transpose W minus 1, I mean you get this part particularly. So, this will be 2 C W minus 2 lambda W, that should be equal to 0, and if I put that C W equal to lambda W, and this is nothing but the eigen equation. As you can see that what the solution demands, it has to be an eigenvector of C. So, lambda is an eigenvalue, and since we are considering W has to be an unit vector, so we will consider the unit eigenvector in this case. And since we would like to maximize the variances, and we would be considering the maximum eigenvalue for the vector corresponding to the maximum eigenvalue. So, what you get actually dominant principal component, that is eigenvector corresponding to maximum eigenvalue of C. Now, what about other eigenvectors, because as you know covariance matrix, it is a symmetric matrix. So, you will get n eigenvectors if because the dimension is small n here in this case, n cross n matrix, small n cross n, and So, all the eigenvectors, in fact, it can be shown that they are providing the maximum variances along the residuals one after another. And so, the solution of this particular analysis, or what we can say, that set of eigenvectors corresponding to decreasing eigenvalues, they provide the principal components. Suppose we represent this set in this form, that there are small n number of eigenvectors, as I say E1, E2, En, such that their corresponding eigenvalues are also in the decreasing order. So, E1 corresponds to the maximum eigenvalue, E2 corresponds to the second maximum, and the minimum eigenvalue lambda n, that corresponds to the eigenvector En. You should note all vectors are normalized here, we are only considering unit vector, eigenvector. So, the ith principal component is defined as the projection along the eigenvector of the centering at S bar, centering at the mean of the data points. So, we can mathematically write it as x minus S bar dot Ei, and so the dimension reduction could be in this way, that we can ignore eigenvectors of small eigenvalues. That means, for a data point we can reduce the dimension, we can ignore those components whose eigenvalues are very less. So, there is an interpretation of eigenvalues, they are representing the variances of the residuals for at that point. So, suppose all the eigenvectors till kth eigenvalue retained for representing data, then the data can be approximately represented by a k dimensional, it can have a k dimensional representation of data. So, we had an n dimensional data, but as I mentioned, the dimension of data is not necessarily the dimension of the space. So, they can lie on a subspace, which is a k dimensional subspace in this case, and using the principal component analysis, we have performed that coordinate transformations. So, now your coordinate axes are given by these eigenvectors, and you are considering, and your center of your coordinates becomes the center of the data point, and you consider the projections of data points along each eigenvectors, that would give you the components. So, first k components in decreasing order, which are sufficient, which may be sufficient to represent the data, which may be sufficient to capture the variances of the data. So, so this is the thing, that we have k dimensional vector, and as you understand, k has to be less than n, or it could be equal n also. So, total variance of data, that can be that can be represented as variances of each component, sum of variances of each component. There are n small n components. So, you consider variance of each component, and that would give you the total variance of data. So, variance is the sum of eigenvalues. So, we can also, this can be shown, this can be proved also, that variance is nothing but sum of eigenvalues. So, that is why the eigenvalue which are very small, which is negligible, it is not contributing to the data variance part, and we can ignore those components. So, ratio of sum of k eigenvalues to total sum, that is the variance of the data, that is the fraction of variance accounted for. So, in dimension reduction, this is what we would be considering, that as high as this fraction is, better is the information content of the data retained. So, this fraction is a fraction, as you understand, it varies from 0 to 1. So, we will be considering a very high value of this fraction, nearly 1, for representing data. So, mathematically we represent this statistics as r square, which is that fraction of variances retained. As you can see that this is not fraction of variances retained, this is a fraction of variances which are rejected. So, it is the sum of those components, variances of those components which are not accounted in your representation. So, this r square should be as small as possible. So, to summarize, the PCA algorithm is that you have an input, it has a set of data points, as we mentioned, that xj, and each data point is a point in the small n dimensional space, and then the output should be a set of k eigenvectors Now, k will be determined by the threshold fraction threshold, that fraction of variances that we are accounting for with that particular factor. So, the algorithm goes like this: you have to compute the mean of data points, then translate all data points to their mean, compute covariance matrix of the set, then compute eigenvectors and eigenvalues, that is in increasing order, then choose k such that the fraction of variance accounted for is more than a threshold. So, that threshold is also a parameter to this algorithm. Usually, the typical value could be say 0.95, 0.98, that means 95% of the variance you are taking care of by this representation, and use those k components for representing any data point. So, let me elaborate these computations using an example. Consider this is a data point, and we want to do PCA on this data point for reducing the dimension of the data. So, all these data points now they are represented as a column vector of a matrix X. There are 5 data points, as you see, all data points are in 3-dimensional space. So, each column vector is a data point. So, 5, 3, 2, 4, 6, 0, these are data points in that 3-dimensional space. Those are the coordinates. So, if I take the mean of those data points, it is all these 3-dimensional points. So, that means mean of those column vectors, your mean is computed in this form. Now, you compute the vectors translated towards the mean. So, you simply subtract mean from each column vector, you will get this particular matrix X tilde, which is representing the translated vectors toward around at mean, and then you compute this particular covariance matrix, which is X tilde transpose. So, if I perform these matrix computations, this is the covariance matrix you get. So, for principal component analysis, what you need to do? You need to find out the eigenvectors and eigenvalues of these covariance matrices. So, since this is a 3×3 covariance matrix and it is a symmetric covariance matrix, you have 3 eigenvalues. It could be distinct, it could be non-distinct, but there will be 3 eigenvalues and correspondingly there will be 3 eigenvectors. In this particular example, we also note the diagonal elements of this covariance matrix. Actually, diagonals they represent variances of components. Say, first component variance is 1.04, that is the translated part around the mean. So, variance of first component is 1.04, second component is 41.6 and third component is 42.24. If you note that the maximum component actually maximum variance is actually in the third component in this particular data set, which has been given in its original form, and also there are high correlations between the factors, because if you note the corresponding off diagonal terms, you will find that these terms are quite significant. So, the total variance could be total variance is the sum of all these diagonal terms. So, if I take the diagonal terms, you can see the total variance is 84.88, and eigenvalues of the covariance matrix, they can be computed, and they are computed as you can see that one of the eigenvalue becomes 0, that is the minimum, but the maximum is 83.3238 in this case, which is quite high and which is capturing almost all the variance of the data. But the second eigenvalue is also 1.5562, which is also it is much less than the first component, but still it has some significant component. So, what we can do? We can represent this data because the third is 0. So, we can represent this data only using these 2 components itself. And let us see what are the and you should note that some of these eigenvalues, they are the same as the total variance of the data. So, the respective eigenvectors with respect to the eigenvalues, that means E1 corresponds to the eigenvector 83.3238. E2 and E3 similarly they correspond to the eigenvectors 1.5562 and the other one is 0. So, we can perform the dimension reduction by considering projections along E1 and E2 only. So, what we will do? We will consider as if they are the basis vectors now, and each basis vectors has the columns E1, E2, E3. It is a similarity, there is it is the same as what we learned for image transform. So, you have a new basis vectors and the original data point can be, their components with respect to these new basis vectors can be computed. Of course, you have to translate towards mean for principal component analysis. So, if I consider the components of translated data points at mean of those original data points, then with these computations we are computing each one of them. So, it is taking care of for each data point, it is computing the translation, it is computing the corresponding corresponding dot product along E1, E2 and E3. So, now this is your new data point translated, and you can see that one of the component is 0, which means now I can represent it in a 2-dimensional space. So, I can represent it, this is a data point, this is another data point, this is another data point like this, ignoring the third dimensions. So, this is a redundant dimension. In fact, if you note the point set what I have given, they are lying in the plane x plus y plus z equals to 10, and that is why since they are lying in a 2-dimensional plane, through principal component analysis, what you could find out that you could find out the plane of where they are lying. In fact, the third eigenvalue that would give you the normal to that plane, and that is why any projection along that direction it is 0, and E1 and E2 they are giving two directions, which those are the vectors which are lying on that plane, and this is a new axis, and in that plane you can once again express the coordinates of each data points. So, this is how using principal component analysis you can find out the lower dimensions on which the data points lie. So, let me stop here and we will continue this topic in the next lectures. Thank you very much for listening to my talk.